All right, let's dive into one of the absolute biggest, most mind-bending puzzles in all of science. We're talking about the search for a single, unified theory of everything. So here's the big question, right? Why can't physics just have one master theory? I mean, we have these incredible theories that describe our universe with just stunning accuracy. So why can't we just smash them together? What's the big roadblock stopping us from getting that one beautiful equation to describe it all? Okay, so that brings us to the mission. What physicists are trying to do right now. It's all about uniting the two absolute pillars of modern physics. You got one for the really, really big stuff in the universe, and another for the unbelievably tiny stuff. And yeah, physicists look at these two frameworks and think, okay, these are our best shots for a grand unification. But man, it is not easy. It takes some serious brain power because at the end of the day, you're trying to weave together two completely different pictures of how reality actually works. But here's what's so cool about this whole thing. Get this. Even if it turns out to be totally impossible to unify them, just the attempt, well, that alone is one of the most productive things happening in science. You know, it really is a case where the journey might be way more important than the destination. When you boil it all down, the goal is actually kind of simple. Well, simple to say, anyway. Each of these theories has its pros and its cons, right? General relativity, it's brilliant for describing gravity, but it just falls apart when you get super small. And quantum field theory, it's a rock star with particles, but it's got nothing, absolutely nothing to say about gravity. So the idea is, hey, let's keep the good stuff from both and just toss out the parts that don't work. And this is a perfect example of why the whole quest is so valuable. Just trying to solve this puzzle has already spun off these incredible new ideas. I mean, we're talking about seriously mind-bending stuff here, like string theory and loop quantum gravity. These are whole new avenues of research that basically popped into existence just from people trying to crack this one problem. Okay, so what is the core problem? Why is this so incredibly difficult? Well, it all boils down to a fundamental conflict, a real headbutting of ideas. The best way to think about it is like this. Imagine you're trying to describe the world, but you have to use two languages that have absolutely nothing in common. No shared words, no shared grammar. That's pretty much the mess physicists are in when they try to talk about something as basic as energy. All right, let's look at team general relativity first. This is Einstein's theory, the one for the big stuff, planets, galaxies, you name it. In that world, energy isn't just a single number you can write down. Nope, it's a whole collection of numbers packed into this special mathematical thing called a tensor. It has to be that way so it can work with all the weirdness of curved spacetime. Okay, now let's jump over to the other side, quantum field theory. This is the theory for the teeny tiny world of particles. And here, energy is, wow, something completely different. It's not a set of fixed numbers at all. It's more like a cloud of possibilities. A probability distribution that just tells you the chances of the energy being here or there at any given moment. And boom, there it is. That's where you can see the conflict crystal clear. You've got one theory saying energy is a bunch of solid numbers in a neat little package, and the other one says it's this fuzzy, uncertain cloud of maybes. They're both using the same exact word, energy, but the things they're describing might as well be from different universes. They're totally alien to each other. And this, right here, is the knockout punch. To put it in the exact words from the source material, the ways these two theories describe energy, they conceptually have nothing in common. Wow. It's not like they're just speaking different dialects. They are using completely different languages, different concepts, for one of the most fundamental things in our universe. So yeah, how on earth do you unify that? So it really seems like we're stuck, right? Like it's an impossible problem. But hold on. What if we've been looking at this whole thing completely the wrong way? That thought leads us to a really radical and honestly super fascinating new idea about what the real goal should be. No, seriously, think about it. What if we're asking the wrong question? What if the goal isn't to somehow Frankenstein our two best theories together? What if the real mission is to dig deeper, to look underneath the theories that we as humans have come up with? This is a huge shift in thinking. The new goal wouldn't be to unify our human perspectives, because that's what theories are, right? They're our models of the world. No, the new goal would be to find the actual underlying machinery of reality, the real nuts and bolts of the universe. So, this totally reframes the problem. You can think of it like a new hierarchy. At the very bottom, the most fundamental level, you have this machinery, the real true stuff that makes up the universe. And then general relativity and quantum field theory, they aren't that machinery. They're one level up. They are just the models, the stories, the perspectives that we humans have figured out from looking at how that machinery works. And that leaves us with one final, totally mind-bending thought to chew on. If this new idea is right, it means that our two greatest scientific achievements, general relativity and quantum field theory, they aren't the final answer. They aren't the ultimate description of reality. They might just be shadows. Shadows on a cave wall cast by some deeper, weirder, and way more fundamental truth that we haven't even begun to discover yet. So, are our best theories just shadows on the wall?